Stanford University.
Thank you, Sally, and thank you, Lee, for the invitation. Really a pleasure to participate in this seminar series because I don't know if there's a better place on campus where you can get a broader view and perspective of the energy issues that we're facing. So it's really a pleasure to be here today. The theme of the talk is the solar conversion of chemicals into a species that we can use as a fuel. So we want to take advantage of sunlight, of which we have much deposited on the face of the Earth, and we want to do chemical reactions. We want to convert chemicals from form A into form B, where we can then transport that, store that, and then use them to provide the fuel once again. In other words, a means of storing solar energy. So that's the theme of today's talk, the synthesis of fuels from sunlight, and we're going to talk about nanoscaled materials for this purpose. I'd like to start with the conclusions of the talk. These are the three main bullet points that these are the main messages that I'd like you to walk away with today. And the first is that chemical fuels are an excellent means to store energy. So developing means to synthesize fuels sustainably would play a major role in solving many of our energy and climate problems. Okay, so we want to find a way to store that solar energy in the form of chemical fuels can only be a good thing. The second bullet point I'd like to make is that fuel synthesis by photocatalysis or photoelectrochemistry can be a cost-effective and scalable on a terrestrial scale means to do this if, and this is a really big if, materials with appropriate properties can be developed. And I'll be going into that second bullet point early in the talk. And third of all, the second bullet point was really what motivates this third bullet, which is our need for fundamental science to attack some of these challenges. There are big challenges both in semiconductors and in surfaces for light harvesting and catalytic transformations. And so I'm going to talk about the approaches that we're using in our lab to attack these problems. So that's effectively the outline for today's talk. Here's really one slide to just elucidate the picture. I think a lot of us are aware of the energy problem. I just want to show graphically our current energy consumption. If it were this little cube, this represents 16 terawatts of power that we're consuming in 2009. This is where we're projected to be in 2050, is consuming about twice as much, which is 30 terawatts. The good news is that we have a lot of solar energy to take advantage of, 89,000 terawatts, in fact. So we don't even need to harvest a large percentage of that energy to be able to meet these needs. And I want to say furthermore, this is what the United States looks like in terms of its solar radiation energy. And you can see that, so red means a lot of sun, and yellow means quite a bit as well. Interestingly, most of the area, most of the landmass of the 48 contiguous states, you're going to be surprised to see this, but it's actually not too different from Hawaii. So we effectively live in Hawaii is another way to think about that in terms of harvesting solar energy. So we get quite a bit of sunlight. So one way to look at these numbers is to say that the sun provides about 4.3 times 10 to the 20 joules per hour of energy. That's exactly our consumption rate on a yearly basis. In other words, the sun deposits as much energy in 1 hour on the face of the Earth as we consume in our society over the course of a year. So the question is, how can we take advantage of it? Because the problem is it's an intermittent resource, and therefore solar energy and storage go hand in hand. Oops. And so what we'd like to do is we want to use chemical bonds as a means to store that energy, and here are two possible reactions that one can think about. Think about splitting water into hydrogen and oxygen. It's uphill by 1.23 eV, electron volts. So clearly water is a very stable substance. If we use sunlight to split it, we can then combust that hydrogen and go the other direction and get that energy back out. Similarly, you could reduce CO2 with water to form, say, methanol or some other alcohol or diesel or gasoline, hydrocarbons in other words, and you can use solar energy to drive that reaction uphill with the solar energy, and then we have this, we can store it, we can transport it. When we combust it, we can get that energy right back out. So that's what we're going to be talking about today. And just to put on a map, I don't know if any of you attended Steve Chu's talk a few weeks back, but he showed a very similar plot, again, advocating really for chemical fuels and specifically liquid fuels. This is what we're plotting here is volumetric energy density, megajoules per liter. And on this axis, gravimetric energy density is megajoules per kilogram. What you see here is that the liquid fuels actually have a lot of chemical energy stored in them, both as a function of volume and as a function of weight. And you can see that they're actually orders of magnitude greater than batteries as a form of energy storage. Not to say that battery research isn't important. Absolutely, batteries will always be a part of our future, but liquid fuels are very tough to beat and a wonderful way to store energy. So now let's say you want to take advantage of the sunlight and you want to produce a chemical fuel. How do you go about doing it? Well, one can be as creative. You can really open up the toolkit and say, you know, I'm limited by my imagination in ways to harvest that sunlight to produce fuels. I'm going to show you some common methodologies that are being employed today. One is photobiologic, in other words, engineering organisms. There are cyanobacteria, organisms that live near hydrothermal vents deep in the Pacific Ocean. There are many ways you can either go down and actually fish out these types of organisms, which have some interesting functionality, or you can engineer an organism to synthesize fuels when you shine light on them. In this case, this is some work at NREL in which they're splitting water into hydrogen and oxygen using some algae. Another methodology is photochemical, so you can actually have chemicals in a solution of water where you shine light on, say, Ru-Bipi, this particular molecule, where you excite an electron. That electron gets transferred into a methylviologen. So you oxidize the ruthenium to 3+. The methylviologen gets reduced from 2+ to 1+. And now this methylviologen is going to transfer its electrons into protons in solution to make hydrogen. And then this Ru-Bipi, which is in a 3+ state, is going to oxidize EdTA to EdTA+. And thus you end up right back with your Ru-Bipi 2+, methylviologen 2+, and you can repeat this cycle over and over. So that's another scheme that you could make, say, hydrogen with these photochemicals. Another way is solar thermal. So there's already processes in place. ExxonMobil, for instance, they developed a process by which they can convert carbon dioxide into methanol. Okay, the problem is that there's a heterogeneous catalysis reaction, requires very high temperatures, requires high pressures, but you could technically achieve that if you have a heliostat like this, in which case you have a number of parabolic mirrors that are focusing light onto a specific point. You could heat that point up to 1500 degrees C if you want, and that would provide more than enough energy to do this ExxonMobil CO2 to liquid fuels process. Another way you can do this is you can grab photovoltaics, which provide electricity from sunlight. We all know this. And then you can just plug those positive and negative leads into a large water electrolyzer, and you're just splitting water by combining an electrolysis unit with a solar photovoltaic. Okay, so these are just different means, and it's again, we're limited by our imagination. There's many different ways that you can harvest sunlight and convert into fuels. What I want to be talking about today is a type of device where you really integrate both of these two into one single device that completes the full function, and that is photoelectrochemistry. And so here's a drawing that was made by a PhD student, Jibo Chen, and you can see here it looks very similar to a solar array. It's really a flat panel, this time consisting of two different types of semiconductors, photoanodes and photocathodes, and they're lying down side by side. You can see that they're immersed in water, and they have some capping plexiglass or glass. The sunlight comes in, strikes the semiconductors, you excite electrons and holes just like you do in a photovoltaic, but rather than extract those electrons and holes, you actually send them to the surface where they're interfaced with water, and you split that water into hydrogen and oxygen. Another way you can do this is you can plug in, let's say, the effluent from a power plant, from a coal-fired power plant, which normally spits its CO2 out in the atmosphere. What if you injected that CO2 into the liquid here, you solvate the CO2, and instead of reducing protons to H2, you hydrogenate the CO2 to make, say, methanol. Okay, so this is the scheme that we'd like to pursue. The question is, has anyone done anything like this before? Is it even possible? Are we dreaming this up? The answer is no. Plenty of people have worked in this field for a long number of years, at least 3 to 4 decades. And this is the world record device that I'd like to present to you. It was developed by John Turner at the National Renewable Energy Lab in Golden, Colorado. And this is a device in which he took a gallium indium phosphide and deposited onto effectively a PN junction gallium arsenide solar cell. And the idea is when he shined light onto this device when immersed in water, he evolved hydrogen here on the gallium indium phosphide surface, he evolved oxygen off of the platinum surface, and he was able to achieve a 12.4% solar to hydrogen conversion rate. Okay, that's taking all the solar energy impinging onto that material. 12.4 of that energy actually came out as molecular H2. So this tells us that, wow, this is actually achievable. It isn't some pipe dream. We can, in fact, split water with no applied bias. Okay, we're not taking electricity from anywhere else. It's just the materials, the semiconductors, doing their thing. Now, the problems with this material are twofold. Number one is extremely expensive. We're talking about on the order of about $50,000 per square meter for that type of material. So clearly, you're not going to be layering this on rooftops or whatnot. Number two problem is it's not very stable. It turns out that there's a cathodic corrosion process that happens on that surface, so it degrades after about 20 hours. But the question then becomes, well, what if? Let's play the what if game. What if I could develop a 12.4% efficient device that could last 5,000 hours, let's say, continuously, that cost something like what SIG solar cells typically cost, let's say, $150 to $200 per square meter to fabricate. Okay, and this is a really important question that I think applies not only to this field, but for any of you guys who work in energy and are working on some type of technology. The question is, if you hit all your targets in the research lab, if it's as efficient as you could possibly imagine, if it's as stable, if it's as cheap, The question is, could you build a plant around it, a chemical plant effectively, that could produce whatever it is that you're trying to produce, electricity, methanol, or what have you? Could it be feasible on a large scale? And that's a question that's not often asked in academia. But it's a question that we asked for this particular case because we wanted to know, because if we find out that we make hydrogen by this way and it turns out to cost $100 per kilogram, then there's no way that's going to be scalable. There's no way that's going to be cost effective. Maybe we better turn our research attention somewhere else. And so I'd like to encourage everybody in the room to think about that for the particular technologies that they're working on. If you hit your research targets in the lab, is it scalable? So we try to answer this question of could a large-scale PEC system ever be cost-effective? How do you start? Well, this is our methodology. We, number one, defined our PEC targets. We defined, hey, if what's our goal in the research lab? When do we declare success in the research lab? And we'll take it from there. So we start with that. Then we brainstorm some reactor devices, some large-scale devices similar to the one I showed you a couple of slides ago. Okay, there's different ways that you can do this on a large scale. So we try to dream these up. We then down-select different types of reactors based on back-of-the-envelope calculations on cost and performance. Then from there, once we figured out which are our primary candidates that we'd like to go forward with, we can design all the auxiliary systems and the conceptual plant. And I'm talking about every heat exchanger, every pump, every compressor, how much did the land cost you, how many people do you need to service this thing, what's the lifetime, all these types of issues. And in the end, you can develop a bill of materials and capital costs. You figure out what the fixed costs are of such a plant, and you can figure out what the operating costs are. And if you know those two things, then you can calculate, and based on your production rate of hydrogen, you can figure out, well, how many dollars per kilogram is it going to cost me to get that hydrogen pure and compressed out the plant gate? All right? And then once you've got that, that's a really nice number to know, then you can go right back to square one and do a sensitivity analysis. You can ask yourself the question, well, what if instead of 10%, what if I could make it 15% efficient? Or what if instead of 5,000 hour stability, I could make it 10,000 hour stable? Or maybe it's only 1,000 hour stable. You can conduct that sensitivity analysis and figure out how this cost of hydrogen out the plant gate changes as a function of your research targets in the lab. Okay, so this is part of what we'd like to start with. And so I'm going to show you 4 different types of reactor configurations that we looked at. By the way, I should go back one slide and mention that all of the full analysis, it's a 130-page report, is published here. This is me working with a number of others, technical people who work in this field together with chemical engineers from a scale-up company. That's what they do. They scale up large-scale systems. And so we worked in concert with them to come up with this report funded by the DOE. So here's type 1, the colloidal suspension reactor. This isn't as fancy as what I showed you a couple slides ago. This is effectively, and I'm not even joking, it's a plastic bag that's filled with water, and it has these nanoparticles floating around. The nanoparticle semiconductors absorb sunlight, and on that nanoparticle surface, some sites create oxygen, some sites create hydrogen. You've got this hydrogen-oxygen gas mix in that headspace above. Doesn't sound very safe, right? So we're a little bit worried about that. But then you want to separate out that hydrogen as fast as you possibly can. You want to compress it, condense it, and get hydrogen into the pipeline under what we called, or what's defined by the Department of Energy as standard conditions for hydrogen out a plant gate, which is 300 psi hydrogen of 99.9 something % purity. So this is the concept of the type 1 colloidal suspension. Again, colloidal suspension of these particles. In this case, it's in potassium hydroxide water solution. And we use these metrics of, let's assume it's 10% efficient. Let's assume a particle cost of 1x, which in this case means $300 per kilogram, which isn't super cheap. It isn't super expensive. And let's say these particles last for 5 years. And these things are literally floating around in bags that are 1,060 feet long by 40 feet wide. This size was determined by how this is a plastic bag that gets rolled up. It's got to fit on the flat bed of a Mack truck. Okay, that's what defined this size. And they're only 10 centimeters tall. So there's just a really thin film of water, really, and then you're shining light in there. You're making your hydrogen oxygen, and this will inflate as you produce your gases. And of course, there's this whole gas capture subassembly. Okay, so this is type 1. Type 2 is a similar concept. You have 2 different types of nanoparticles now, and if you want to avoid hydrogen and oxygen being in the same gas space, you can separate them. You can have one bag that makes exclusively hydrogen and another bag that makes exclusively oxygen. And what you're using here is you have some sacrificial species that go back and forth, change their redox states in each bag. So in this case, when you reduce protons to hydrogen, you have to oxidize that something else, and then that something else transfers over by some bridge into this other bed where it gets reduced and along with that reduction process, the water gets oxidized to O2. So this way you can have two different types of particles that actually relaxes a lot of the constraints that you need on your materials, which we'll get into in a minute. But in the end, you produce your hydrogen and your oxygen. In this case, we just said the oxygen gets vented out into the atmosphere. Again, you compress your hydrogen. You don't need to separate it because it's pretty pure to begin with. You get your hydrogen out the plant gate. The fact that there's a bridge here where you need this connectivity actually changes a lot of the dimensions of the baggies that I just described before, but they're still 200 feet long by 20 feet wide. And note that the efficiencies have all dropped by half compared to the last slide because now you need twice as many photons to get the same amount of hydrogen out. Okay, type 3 is now we're going to get away from these colloids, these suspended nanoparticles. We're going to talk about thin films, sort of like the figure I showed a few slides ago with Jabot's drawing. That's effectively what this is. It's just a flat device that accepts solar photons. It's immersed in water, splits hydrogen and oxygen on two different faces. So you have instant separation, so then it's easy enough to just compress and get hydrogen out the plant gate. This effectively looks like solar cells, just like a solar cell array sitting on a rooftop. They're tilted at a 30-degree angle to maximize the amount of solar photon absorption. I should say that the efficiencies here are baseline is 10% efficient, $153 per square meter, which basically comes from the SIGS world, and a PEC lifetime, again, we're dreaming here, 10 years. That material doesn't exist, but these are absolutely possible. Okay, if we can do our research and development right, we can actually ultimately produce these types of materials. We're just not there yet. And then finally is that same type of device design, but now we're going to use concentration. We're going to put some parabolic mirrors that are going to accept that sunlight and send it down into our photoelectrochemical material. We don't need as much material now because we're concentrating that light and we're heating it up as well, which makes it easier to split water, so we can go with higher estimates on what the efficiency of such a device is, but it's going to be a little bit more costly because this device needs to, it's actually pressurized in situ. And so this device is sitting on a 2-axis gimbal so that you can be constantly tracking the sunlight. So now that you've seen these 4 different types of reactors, the question is, number 1, how much does hydrogen cost out the plant gate per kilogram? And number 2, how sensitive is that cost going to be to efficiency, to stability, and to the cost of your material? So again, here are the assumptions that are going into the material, and let's look at the Techno-Economic Assessment. I want to remind you here, many of you might be aware of this, but 1 kilogram of hydrogen is the energy equivalent of 1 gallon of gasoline. So when I say a kilo of hydrogen, and this is what the price is, think to yourself, would I be willing to pay that at the pump for a gallon of gasoline? And the first thing so we're looking at the type 1, type 2, type 3, type 4 reactor configurations. And I'd like to point out from a bird's eye view, first of all, you can see numbers as low as $1.49 and numbers as high as $18.75. Okay, that's a pretty reasonable range to be in, all right? We don't want to be paying $20 per gallon, but the $1.49 looks pretty decent. So interestingly, this baggy concept with the colloidal suspension of particles turns out to be the most cost effective. There is, of course, the safety issue of having both hydrogen and oxygen in the gas phase, but you see it's basically $1.65 or so, and the sensitivities to efficiency, sensitivity to particle cost, sensitivity to lifetime, it's not very sensitive at all. So you just need some decent colloidal suspension of a material, and you can produce hydrogen at less than $2 a kilogram. That's like $2 for a gallon of gasoline. That sounds pretty good. Type 2 is going to be more expensive. It had that ion bridge that I described earlier. You need more land area because you need twice as many photons, so it's going to be inherently more expensive, but it's still, the numbers are pretty reasonable and not super sensitive to the materials development. The third type, the planar electrode, is definitely more expensive than these two. You still can reach this kind of $2 to $3 to $4 ideal cost for hydrogen out the plant gate, but it's going to take a very efficient material, and it's going to take a very durable material and a very inexpensive material to begin with. You can see that the sensitivities are huge. It's very sensitive to all 3 of those factors. And then type 4 with the solar concentration, it's basically, again, taking type 3 and then adding a parabolic mirror as well as some solar tracking technology. And you can see that the numbers are looking very favorable down in the 285 to 385 range. So what's the bottom line? What's the take-home message from the techno-economic studies? This tells us, number 1, that this is a scalable technology. Okay? This tells us that we can, in fact, produce hydrogen in a very large amounts. We were looking at tons per day for these 1 ton per day modules. Of course, you can scale these modules. You can grow them. There's no physical limit. It's just how much sun do you have to work with. So the question really becomes, can you develop the appropriate materials in order to accomplish that technological gain? And so this is what inspires our fundamental research to overcome these particular challenges. So let's look at these materials challenges. Let's look at photoelectrochemistry in more microscopic detail, what's happening inside the semiconductor and at its surface in order to drive these reactions. So the first thing I'd like to point out is the solar spectrum. Okay, that's what we have to work with. There's no two ways about it. The good news is that if you take a look, this is the radiation energy as a function of wavelength or as a function of photon energy. The good news is that here's your 1.23 EV line, right? That's our thermodynamic minimum requirement needed to split water into hydrogen and oxygen. Notice that most of the solar spectrum actually lies in higher energy than that 1.23 EV. So that tells us that we've got a lot of radiation to work with. The question is how effectively can we? So now that we know that the sun provides us with enough energy, let's take a look at the redox potentials for hydrogen and oxygen. Okay, this is where the 1.23 volts comes from. Now, I want you to also bear in mind that this hydrogen evolution potential is very similar to the redox potentials for CO2 reduction. Okay, so you could almost instantly swap out, instead of this line being hydrogen evolution, it could be CO2 to methanol, it could be CO2 to ethylene, it could be CO2 to diesel. Okay, it could be CO2 to just about anything, and it's going to be more or less at the same spot. Here's your semiconductor. We immerse a semiconductor inside of an aqueous electrolyte. And you can see this is the conduction band of the semiconductor. This is the valence band of the semiconductor. You form this junction right at that electrode-electrolyte interface. And that's actually a very important junction because that means when we shine light into the semiconductor, when we excite an electron from the valence band into the conduction band, we have an electric field right at that interface which is going to allow us to pull our electrons and holes apart so that we can actually do redox chemistry. We can do reduction on this side, and we can do oxidation down here. So what are the things that we care about for our semiconductor? First and foremost is absorbance. We want it to absorb a good fraction of the solar spectrum. Now, to absorb a large fraction of the solar spectrum, you want a small band gap, but the problem with the small band gap is if it gets too small, then it's going to be underneath the 1.23 volts that you need to split water. So that's going to be a hard limit on one side. So you say, okay, well, I want a bigger band gap so I have more photovoltage with which I can then split water. Well, that's true up to a certain point because as your band gap gets higher and higher, at some point you don't absorb enough sunlight to make for an efficient device to even hit 10%. So we're going to use these as hard limits. You really want your band gap to be somewhere between 1.23 EV and 2.5 EV, and that way you can get a lot of solar photon absorption and have photovoltage needed to split water or reduce carbon dioxide. The magic number in this field typically is considered to be around 1.8 to 2 EV. So that's the first step, is absorbing a photon to create an electron-hole pair of the right energies. The second issue is charge transport. Just because you excited this and you got an electron and hole pair doesn't mean they actually get to the surface to be able to do some redox chemistry. So we also have to think about how we can move these charges so they can reach their respective surfaces to do the work we'd like them to do. We also have to think about the band structure energetics, meaning it's not just the band gap of the material that we think about. So in the solar photovoltaic world, that's all that people need to think about is where are my band edges, or sorry, what is my band gap of the semiconductor? Here, we're actually trying to drive redox reactions of very specific potentials versus some absolute scale or some reference scale. And our conduction band better be high enough such that when we excite an electron, that electron will go downhill to reduce protons to H2. And our hole left behind is low enough in energy such that we can pluck electrons from water to make O2. So it's not just what the band gap is. We have to know physically where are these bands located versus the redox potentials of interest. And then just because you have an electron and a hole at a surface of the right energy does not mean you're going to turn over that reaction. Okay? We have to think about the surface itself. We need to develop materials in which we can maximize that interfacial electron transfer so that we can turn over as many waters or CO2s as we possibly can. So we have to think about the surface as well. And then, of course, there are the practical issues of stability, cost, non-toxicity. If I were to summarize all of these processes in one statement, I'd say there's no material ever known on the face of the earth that satisfies all of these criteria simultaneously. There are plenty of materials that satisfy several of them simultaneously, but you need all of them to be satisfied simultaneously to make for to hit these technological targets that I described earlier. So, of course, you have to start somewhere, so let's take a look at some of the semiconductors that have been studied quite a bit in the past. These are the valence band and conduction bands of a number of garden variety semiconductors that you'd likely to come across. We have hydrogen evolution and oxygen potentials shown on this diagram, and the first thing I'd like to point out is very few of these semiconductors actually straddle the redox potentials, of hydrogen and oxygen. That's a necessary requirement, as I was describing earlier. Those that do typically are very wide bandgap semiconductors, like silicon carbide with 3 electron volts. That means it only absorbs UV light. That's not going to cut it in terms of efficiency. The smaller bandgap materials, like say gallium arsenide, their band edges are located too high. That's true for silicon as well. Cadmium selenide is an interesting one. It has about the right bandgap of 1.7 eV and happens to straddle the bands, but it falls apart in solution. So that's no good either. We're going to be talking about molysulfide in a minute, so I just wanted to point out this is what molysulfide's bandgap looks like. It's a bit small at 1.2 eV, and it's actually a little low with respect to the hydrogen evolution potential. So bear that in mind. Okay, so a lot of research in this area has really been predicated on the thought of creating a material, a semiconductor, that can in fact satisfy all of these requirements simultaneously. But in our lab, what we're doing effectively is we're going to dissect the problem. And I'll tell you why, because I believe very firmly in this statement. I'm happy to be proven otherwise, but I'm going to read this out to you. If you expect a semiconductor to have an appropriate bandgap with exactly the right placement of the valence and conduction bands, plus a high mobility for electrons and holes, and in addition to all that, an optimal surface to catalyze hydrogen evolution, oxygen evolution, or CO2 reduction, then you're asking a lot of your semiconductor. Okay, there's no physical reason why such a material couldn't exist, but what we're going to do is we're going to dissect this problem into really 2 general areas, and that of semiconductors and that of surfaces, and we're going to try to develop these types of materials independently and then interface them together to make a device. So in terms of the semiconductors, what are the questions we're looking to answer? How do you tune the bandgap and band positions of a semiconductor? I showed you a number of garden variety semiconductors. There's very few semiconductors on Earth that have the right band positions to begin with, so really finding a way to engineer the electronic band structure of a semiconductor would be very useful, as well as ways to improve the charge transport. And then there's the development of surfaces for reduction reactions. You need to evolve hydrogen effectively, reduce CO2 effectively. And both of these reduction reactions, guess what they need? They need electrons and holes. So the question then becomes, where do you get your electrons and holes from? You don't want to oxidize methanol in order to produce methanol on the other side. That makes no sense. We'd like to oxidize water because it's free and abundant. So we want to improve catalytic activity for water oxidation, which is otherwise known as the oxygen evolution reaction. And then, of course, we want to stabilize the surface and prevent corrosion of our semiconductor. So this is the outline where we're heading from here. I'm going to first tell you about some of the approaches we're taking on the semiconductor side of the equation, and also bring up the issue of hydrogen evolution and stability in concert with that. Then we'll talk a little bit about the oxygen evolution reaction and the challenges therein and the approaches that we're taking. And then we'll finish up with CO2 reduction and some of the ways that we're attacking that problem. So let's start with the semiconductor side of the equation. So what are common approaches that people have used? I mentioned that people have really, this whole field has been predicated on finding that one material that can do it all. So people really take something that works reasonably well in some sense and then try to improve it. And so examples are, for instance, take titanium dioxide, which works beautifully with UV light. Zinc oxide works beautifully with UV light. And the question is, how can you make it absorb more solar photons? Well, people have accomplished this ultimately by a doping and alloying approach, by incorporating, say, nitrogen into that TiO2 lattice, incorporating cobalt into the zinc oxide lattice. Here's some data. Here's a UV-vis absorption spectrum. You can see pure zinc oxide in here doesn't absorb until you get to 400 nanometers, which is UV light, and then it absorbs light extremely well. By incorporating cobalt into the lattice, you can actually move that. You can shift the onset of absorption. You can redshift it so that you're absorbing more of the solar spectrum. So that approach has certainly been shown to work in terms of absorption. What often happens, unfortunately, is by putting dopants into these lattices, you oftentimes kill the charge transport property. So yes, you excite many more electrons and holes than you otherwise did in the sun, but then these electrons and holes can't make it to the surface. They end up recombining at these defects, and you don't get that energy out of your system. So although there's been a lot of gains here, there haven't been as great as one could hope. Another approach that people have taken is using tandem cells, or in other words, multiple semiconductors, and this is exactly what John Turner did in that world record device. I mentioned he used a gallium indium phosphide p-type photocathode. You can see that the band positions for gallium indium phosphide are too high to split water. They're fine for the hydrogen evolution reaction, but these holes that are generated are not deep enough to pull electrons from water. So what did John Turner do? That's why he layered it on top of this gallium arsenide underneath it. That gallium arsenide effectively gives it a photovoltage boost, so that this hole no longer has to oxidize water to oxygen. Now that hole combines with a photogenerated electron from the gallium arsenide. So you lose that efficiency. You take an efficiency hit there because you're recombining your electron and hole, but now you can use this hole on your counter electrode to oxidize water. So that's another approach that one can take. So our approach, we're going to look to a different approach than one that has traditionally been used in the literature, and that is that of quantum-confined semiconductors. And the idea here is that if you take a semiconductor and shrink its size below what's known as the Bohr-exciton radius, you can actually increase the band gap of your semiconductor. So we're going to go the different direction. Instead of taking, say, TiO2 or zinc oxide, which are wide bandgap semiconductors, and we're going to mix in some other elements to alloy it and then make for a smaller bandgap and increase the light absorption, we're going to start with something that has a bandgap that is too small to begin with, but as we shrink the size of that semiconductor, we expect that we can widen the bandgap to hopefully hit the target of 1.8 to 2.0 eV that I described before. And of course, what happens when you widen the bandgap of the semiconductor is you take a look at the solar spectrum. As you widen the bandgap, you're going to be decreasing the amount of photons that you absorb. But on the plus side, you're going to have greater photovoltage. And likely, you're going to have improved match to the redox potentials of the reactions you're looking to drive in solution. So this is the interplay that we're looking to take advantage of. Now, you can't take advantage of this method with a lot of semiconductors, like TiO2. Quantum confining TiO2 is not going to gain you anything. Its bandgap is already 3 eV. You widen it, now it's 4 eV. You absorb even less photons. That's not its issue. But so we looked into the literature and said, well, what kind of semiconductors out there might this approach be amenable to? And so really the dichalcogenides seemed particularly interesting to us. Here's a number of them listed. And you can see that the valence and the conduction band of these semiconductors, for the most part, are not that far apart. They're about 1.5 EV, so they're pretty narrow gap semiconductors, which is good. You don't want to start with something that's really tiny semiconductor, otherwise, or tiny band gap, otherwise you really have to make it a small particle to quantum confine it enough to reach the 1.23 volts. So these are right in about the right region. Also, you can see that the band mismatch, it's not an ideal placement of the valence and conduction band, but it's close enough such that a little bit of quantum confinement should get you to be able to straddle those bands. So we looked at these, and tungsten sulfide and moly sulfide really came out to us because they're very earth-abundant elements. They're also known to be good hydrogen evolution catalysts. So we said to ourselves, well, if we can get these semiconductors to absorb a good fraction of the solar spectrum and pump electrons into that surface, they should be good catalysts as well to turn over H plus to H2. And here's an example of the quantum confinement effect. This is with a different chalcogenide. This is with cad selenide. This type of work there are a number of images like this that you can find because it's a classic case where the cad selenide, as I mentioned before, has a band gap of 1.7 eV in the bulk. That means that when you shine UV light, it will fluoresce out photons at 1.7 eV, which is red light. And as you make them smaller and smaller down to 2 nanometers, you get quantum confinement in this particular case, and you can widen the band gap up to about 2.8 eV. So this is the effect that we're taking advantage of. It turns out that there was a researcher at Sandia National Labs, Jess Wilcoxon, who had studied quantum confinement in this particular system for the photooxidation of phenols. And what I've done is I've taken one of his images out of his paper and basically drawn the redox potentials for hydrogen and oxygen and shown that, yes, this is where bulk moly sulfide sits, but his 8 to 10 nanometers is quantum confined, as you can see here, just about to straddle the bands. And as you go to 4 to 5 nanometer MOS2, now you've definitely straddled the redox potentials of hydrogen and oxygen. So this tells us that there's promise in this method. But nanoparticles are a good place for us to start. In the end, what we'd like to go with is, well, we'd like to start with nanoparticles that are layered onto a substrate. We don't want them touching. As soon as they start touching, you lose the quantum confinement effect because now the wave functions of the two particles are overlapping at that interface. So we need to keep them discrete from one another, and we need to really keep that size monodispersed. We have to make sure that we don't have a wide disparity in size. Otherwise, it's tough to understand the optoelectronic properties of a given size of the material. Although this is great to start off the study, in the end, what we'd like to do is we'd like to look into other morphologies that we think are more appropriate. And the reason why I say that is because if you imagine 5 nanometer nanoparticles of moly sulfide sitting on a surface, if you shine light onto that, how much light are you really going to absorb in a 5 nanometer nanoparticle? Not all that much. And so what we'd like to do is we'd ultimately like to, say, grow nanowires that are of that dimensionality. They're quantum confined in the XY plane, but not in the Z plane. And that way you can orthogonalize the light absorption path length with the quantum confinement effect. So nanowires might be more useful, planar structures, vertical planar structures, mesoporous materials. As long as the feature size here is below that Bohr-exciton radius, which in the case of moly sulfide or tungsten sulfide turns out to be 12 nanometers, we should see this effect. So that's our working hypothesis. So how do we go about synthesizing MOS2 nanoparticles? So we start off by taking a block copolymer which has two different sides. It has a polystyrene tail and a vinyl pyridine head. And we dissolve this inside a hydrophobic solvent, and you get an assembly such that the hydrophobic tails are extending outwards and the hydrophilic core is shielded on the inside. Then we add a molyacetate precursor. This prefers to be in the hydrophilic part of the micelle, so the moly precursor migrates here into the middle. We end up forming these micelles that are loaded with metal right there at the core. Then we dip coat any substrate we want into that solution, and we pull out a flat surface with micelles sitting shoulder to shoulder, each micelle containing these metal cations. But then we need to get rid of the organic if we want to make a nanoparticle out of this, so then we just oxidize this in an oxygen plasma, which is a fairly low temperature technique. We can get rid of all this organic matter we're left behind with this particle, which we can then further oxidize to ensure that we have a pure MoO3. And then from there, we can put these particles, which are supported onto any support of choice, in a furnace, 10% H2S, 90% H2, roughly 1 hour at 200 degrees C, and voila, you end up with MoS2 nanoparticles. So let me show you some images. These are some AFM images of the MoO3 moly oxide nanoparticles immediately after the oxygen plasma step. We reduce these in the hydrogen H2S to sulfidize them, and you can see that the particle size has changed a little bit, likely due to a change in the lattice constant of MoO3 versus MoS2. It shrinks a little bit, but you can see that they haven't sintered, and that's a very important point. When you heat things up, oftentimes these nanoparticles are mobile and will agglomerate, but you can see that that has not happened. We use X-ray photoelectron spectroscopy to keep track of the oxidation state of our materials before and after the furnace treatment. And so we can see that beforehand, this is from this image, we see a very clean signal for MO6+, MoO3 in other words, which is exactly what we'd expect. After sulfidization, we asked ourselves the question, well, yes, you might form the sulfide in the furnace, but what happens when you pull it out and expose it to air? Because air is pretty oxidizing. Oxygen, in other words, is a strong oxidant. And we're a little bit concerned that these nanoparticles might be oxidized right at the edge. But the XPS, which is a very surface-sensitive technique, tells us that that's not happening whatsoever. This is a characteristic right on the money, moly 4 plus sulfide. You can see sulfur also in the 2S peak emerge, and we don't see any signal whatsoever coming from an MoO3 as we had seen previously. So this is very convincing that we've made MoS2 nanoparticles. Our images tell us that they're discrete and they're not getting oxidized in the air. So now that we have this method down pat, what we've done is we're changing the block copolymer. That's one of the convenient points of the synthesis. By changing the chain length of the polystyrene tail versus the polyvinyl pyridine head, and by changing the loading ratio of how much metal we put into our solution, dissolve in our solution, we can get changes in the nanoparticle size. So we can increase the weight of the block copolymer and get larger particle sizes out. These are AFM images up here, confirmed by SEM images. And you can see that the range of nanoparticle sizes we're looking at, 5.5 nanometers, 9 nanometers, and then a couple that are around 25 nanometers in size. So now that we've got these supported, now we want to measure UV-vis absorption on them. We want to see, is there a blue shift in the band gap as we expect? So here's the absorbance spectrum as a function of the photon energy. This is a bulk film. These are the nanoparticles. And what I want to show you is that as a function of size, as we go to smaller and smaller size nanoparticles, you see two effects. First of all, you're getting less and less absorption of light, which is expected because the particles are smaller, there's less optical path length. But you also see that the onset for absorption is shifting to the right, which in this case means it's a blue shift in the onset of absorption. So we can take this data, and then the more formal way to calculate the band gaps of these materials for an indirect band gap semiconductor is to make a Tauch plot, which is the absorbance times h nu to the 1/2 power versus absorption. And you can see here we extrapolate down to retrieve the band gaps of our semiconductors. And in fact, what this data is telling us is that we've quantum confined. This is our measurement from the bulk. These are the nanoparticles in terms of decreasing sizes down to 5 nanometers. We've been able to widen that band gap to 1.8 eV, which is exactly the target that we were shooting for. So now this isn't quite enough because, as I mentioned, this is still a sub-monolayer of nanoparticles. It's not a lot of material, so when you shine light on it, you're not going to get that much light getting absorbed by your semiconductors. So what we've been doing instead, actually, is we've been taking these exact same nanoparticles and we've been impregnating them onto a scaffold, a three-dimensional scaffold that we synthesize by sol gel chemistry. We literally make a sol, we use filter paper, a piece of filter paper as a template, we burn off the filter paper, and we're left with indium tin oxide, macroporous structure of indium tin oxide sitting on top of glass. And so this is conceptually what we're trying to do. We're trying to load the nanoparticles, and this is what it looks like by SEM. You can see that these are very large pores. They don't have to be small. In fact, we don't want them to be too small. Otherwise, diffusion of water in and gases out might be problematic. But nevertheless, we've taken this structure, and this is what we're going to use to measure hydrogen evolution and photoelectrochemistry on our nanoparticulate semiconductors. So in terms of hydrogen evolution, so this is an experiment we did in the dark. So I want to point out this is a cyclic voltammogram in which you're looking at, this is potential versus the standard hydrogen electrode at pH 0, which means that at 0 volts is where the thermodynamic limit is for reducing protons to H2. We're looking at 3 pieces of work. This is a single crystal moly sulfide that was published by Trebuchet in 1977. A few years ago during my postdoc, we looked at moly sulfide nanoparticles that were produced in vacuum, particles that look just like this by STM. And you can see that these are extremely active because the hydrogen evolution current is very close to the equilibrium potential of 0. And these are the nanoparticles, the 25 nanometer variety that we've prepared and impregnated onto that transparent conducting oxide. And you can see that these are certainly active for hydrogen evolution, though not quite as active as these UHV prepared nanoparticles, which we think might have to do something with some folding. And this is some recent work that was published from a group in Israel, in which case they find that moly sulfide often likes to fold up over on itself. And the work that we had done in Denmark, we had really elucidated that it's the edges of the moly sulfide that are active for hydrogen evolution. If this thing folds up and forms an onion-like structure, you don't have edge sites anymore. So this is something that we're looking to ultimately control. We think we can improve that onset into this vicinity so long as we can keep these nanoparticles unfolded. In terms of photoelectrochemistry, this is what our cell looks like. It's a standard 3-electrode electrochemical cell where we shine light from a solar emulator. And what you're looking at here is this is the signal coming from our bare substrate. When we load up our nanoparticles, you can see little bumps. These little bumps are coming from photocurrent when the light is off versus the light is on. And we're zooming here to this particular section. You can see when the light is off, there's a dark current. When the light is on, we get some photocurrent. The difference between these two is approximately 200 nanoamps. Certainly not enough to save the world, but certainly enough to prove to us that these are photoactive semiconductors despite their small size. We're able to absorb sunlight and transfer them to do photoelectrochemistry at the surface. Very interestingly as well, this current, if you notice, is a negative current. It goes more negative, and in our convention, more negative current means it's a p-type semiconductor, or in other words, it's a cathodic reaction that's happening on the surface. It's hydrogen that's being evolved most likely on that moly sulfide surface, and that's exactly what we'd like to do, because photooxidation would be a major problem with the sulfides, so we want them to run as a p-type device, sending electrons to the surface for hydrogen evolution, where they are, in fact, stable. Okay, so that's some of our work in terms of MOS2 and what we've been doing in terms of quantum confinement as an approach to tailor the band structure of semiconductors so we can widen the gap, hopefully, to whatever value we want. We can dial it in terms of size. We know that these are active nanoparticles for hydrogen evolution, though we think we can make them even more active. But that's only one part of the picture. We need to think about what's happening on the other electrode. In this case, it's the oxygen evolution reaction, because again, that's your source of protons and electrons. So this is the reaction we're looking to drive. We're looking to take water and make O2, but I'm using a fuel cell to show off maybe a bigger picture, a way of looking at oxygen electrochemistry a little bit differently. So many of you are aware of what fuel cells do. You have fuel coming in on one side, typically hydrogen. It gets oxidized, you make protons. The protons scoot across a membrane where they're then used to reduce O2 to H2O. So a fuel cell is a device where you put chemical energy in terms of fuel on one side and oxidant on the other, and you get energy out of the system. You can also run the fuel cell in reverse. You can also run as an electrolyzer. In other words, this is putting chemical energy in to get electricity out. You could also put electricity in and get energy out in the form of chemical fuels. So instead of, say, oxygen reduction to water on this side, now you can crack water and make O2. The protons then go the opposite direction, where in this cathode, they're reduced from protons to H2. And so this is a type of device, actually, of which now we can think beyond solar energy. What if you wanted to couple to, say, wind energy? You could use this type of a device and plug it directly into a wind farm to help buffer its electricity capacity. In other words, one of the problems with wind farms is that, of course, wind is a very intermittent resource. And when you're cranking out, when the wind's blowing strong, you might be cranking out lots of electricity, but the grid is just not, it can't make use of that electricity. So what do? If you couple it to a fuel cell like this, which can run in both directions, then when the wind is blowing very strong, you can oxidize water and produce H2. You use that H2 as a buffer. It's stored. Whenever the wind dies down, you can run that H2 back the other way as a fuel cell and get your electricity out. So the reason why I want to bring this concept up is the theme here is electrocatalysis involving oxygen. So water oxidation is something that we certainly need for PEC, but I'm trying to open up the picture and say, well, if you can oxidize water well, shouldn't you be able to reduce O2 to water? It's exactly the same chemical reaction, it's just running in opposite direction. And so that's kind of a bigger picture approach that we're trying to take. And I want to just point out the best catalysts that are known to humankind for these reactions. Fuel cells, of course, contain a lot of platinum. Platinum's fantastic for both oxygen reduction and for hydrogen oxidation. However, platinum turns out not to be that great of a catalyst for water oxidation. So ruthenium and iridium are quite a bit better than platinum. So people who have actually developed devices like this, they actually load up on the left side of the fuel cell, on the oxygen side of the fuel cell, they load up not only platinum, but lots of iridium or ruthenium. And when it's operating as a fuel cell, it's platinum that's doing the work. And when it's time for water oxidation, it's the ruthenium or iridium that's doing the work. So now I want to point out, I'm going to be presenting some data of this variety, and I just want to make sure that we're all on the same page on how to read these plots. This is a current voltage curve with the equilibrium potential here pointed out for oxygen electrochemistry at 1.23 volts. That means if you're to the oxidation side, if you're on the positive side of 1.23, you're going to favor water oxidation to O2. If you're on the left side, or the cathodic side of that equilibrium potential, you're going to favor O2 going to H2O. This current means, zero current means that nothing's going on. If you see a negative current, that means it's a reduction current, i.e. if we're going to follow platinum, so this is platinum that we've prepared in our laboratory, you can see here that nothing is going on until you hit an overpotential of 0.25 volts beyond equilibrium. That's just lost energy. And then you start reducing oxygen to O2, and then you hit some diffusion limited current density based on how much O2 can reach your platinum surface. If we swing to the other side, a positive current means you're doing oxidation. So this means you're oxidizing water to O2. So we're looking for a bifunctional electrode. That's really what we're after. We'd like to develop a bifunctional electrode that can do both of these reactions efficiently, and that is exactly what this blue line represents. That's a reversible oxygen electrode. It means that right here at this equilibrium point, you just go a little bit to the left or a little bit to the right, and you're going to get oxidation on one side and reduction on the other, as opposed to, say, platinum, where you have to go significantly far from the equilibrium potential in either direction to get either reaction to go. And so to the kinds of materials that we're really interested in here, we're interested in non-precious metal materials, which would be, of course, ideal. And for inspiration, we're looking to nature. And what we're looking at here is the Oxygen Evolution Center in Photosystem 2. So this is how plants make the protons, or they strip the protons and electrons from water so that they can do their CO2 reduction chemistry and grow. This is what the complex looks like. At least this is a model that was produced by Per Sigban in Sweden. We can see that this has 4 manganese, 4 oxygens forming a distorted cube along with a calcium. And so we asked ourselves the question, well, perhaps there's a way to emulate what Oxygen Evolution Center does, but in a hard material, in something that's more robust and more commercially applicable than an enzyme or a protein that you would end up putting onto a surface. So we looked into literature for manganese oxides, and this is a volcano plot that shows the activity for oxygen evolution reaction, water oxidation. You can see here again, ruthenium and iridium are the best. Platinum's very good. Not quite as good as these two, though. And then there's manganese oxide, which is not such a bad catalyst as well. Though this is a nominal MnO2, and we're asking ourselves the question, can you tune the surface chemistry of manganese oxide so that you can really improve this number? So this is a nominal MnO2, but there's many different phases of manganese oxides out there. So we're trying to understand how to control that surface chemistry. And so let me show you a picture here. This is a big picture of electrocatalysis involving oxygen. We're looking at, we want to take 2 water molecules and we want to oxidize them to O2. And to do this, you're going to require 4 transfers of electrons along with 4 transfers of protons. In other words, these are the electrons and protons that you're pulling from water to make O2. And the point that I'd like to get across is if your electrode is sitting at 0 volts, That means you're 1.23 volts away from the equilibrium potential. That means that for you to go from this point to this point, you have to climb 4.92 electron volts in energy to get this reaction to go, just by thermodynamics. Okay, that's the absolute minimum. And the question that I'd like to ask you is, well, if you could design any catalyst in the world, and these are the intermediates that we're dealing with, OHs, OOHs, et cetera, to go all the way from H2O to O2, you don't want to hold any of those intermediates too tightly or too weakly. Otherwise, you're going to find yourself at some point where it's really hard to go from one step to the next. And another way of me saying that, let me give you a more physical example, is imagine if you're standing on this platform and you want to go 4.92 meters up to the next floor. And I gave you 4 stepping stones that you can use to get from this point to this point. And I said you can choose any step heights that you want to get from here to here. What step height would you choose? Well, you would say, I want each of my steps to be 1.23 meters tall. Why is that? Because then each step you take is exactly 1.23. If you said, I want to take it easy on my first 3 steps and go, say, half a meter on those first 3 steps, that gets me 1.5 meters high. I still have 3.5 meters to go on that last one, which is a really tough step for me to do. So that's exactly how we think about catalysis. We don't want any of these steps to be too high or too low. We want them all to be of equal height. And so that's what we call optimal on this plot. The heights are evenly spaced at 1.23 eV. We can see that ruthenium oxide is actually very close to optimal. That's the black line that you see here. MnO2 is not optimal at all. You take 3 really big steps, so big, in fact, that the last step turns out to be downhill energetically. And then here are 2 different structures of that manganese oxide complex at Oxygen Evolution Center. And that is, and these 2 DFT calculations show that it turns out that the Oxygen Evolution Center is very close to optimal, even more close than ruthenium oxide. So our question is, well, again, this is MnO2. What about exploring phase space that's outside of MnO2? And our hypothesis is, if we go back one slide and just take a look at the Oxygen Evolution Center, during operation, these manganese are either in a 3+ or 4+ oxidation state. So this is what inspired us to try to study these particular materials, really mixed phases of Mn2O3 and MnO2. And so we've really explored that phase space quite a bit. I'm going to show you our best result for our manganese oxide. These are, again, linear sweep voltammograms, very similar to what you saw before. Oxygen reduction happening here, cross the equilibrium potential, oxygen evolution on this side. And we're going to stack up our manganese oxide catalyst against the best catalyst known in the world: platinum, ruthenium, and iridium. And what you see here is the manganese oxide in pink is, for oxygen reduction, it's better than ruthenium and iridium and almost as good as platinum, off by just 0.1 volts. What about on the oxygen evolution side? We can see that the manganese oxide, again, and now it's actually quite a bit better than platinum, not quite as good as iridium or ruthenium, but again, it's only about 100 or 150 millivolts off. So this manganese oxide, by changing the synthetic parameters, by changing the structure of that manganese oxide surface, by changing our processing conditions to heat it to form the right phase, we've been able to make extremely active catalysts for both oxygen reduction and oxygen evolution on a non-precious metal material. So I'm going to skip a few slides here where we went up to the synchrotron up in SLAC to understand what the phase was of our manganese oxide during operation. And this is the slide that really sums up that work. When we synthesize our manganese oxide, it is mostly MnO2 with a bit of Mn2O3. After we heat it to this specific temperature of 480 degrees C, we've been able to enrich the Mn2O3 phase. After doing electrochemistry during oxygen reduction reaction, we don't see much of an effect from the as-synthesized sample. It's predominantly Mn2O3. But once we take it out to oxygen evolution potentials, which are very oxidizing, we actually see a change in the phase to MnO2. So this tells us that there's phase transformations. It's basically a different manganese oxide surface during the oxygen reduction fuel cell reaction versus the oxygen evolution reaction. And what we hypothesize, just taking a look at this CV for the aficionados out there, we're looking at onset of ORR, onset of oxygen evolution. We see that there is a phase transformation, Mn3+ to 4+, right at that potential where oxygen reduction occurs. And so we hypothesize by changing our material, by changing the nanostructure of our material, we can actually change this equilibrium potential for the change in Mn2O3 to MnO2, which will then allow us to tune this onset potential to the right, which is where we want it to be. to make for a better fuel cell catalyst. I'm going to take just 2 minutes to finish up some work we've done on CO2 reduction. And one of the big points that I tried to make earlier is that we have, if we look at the equilibrium potentials for CO2 reduction to different molecules you might be interested in making, say ethanol, ethylene, methane, et cetera, these potentials are very close to zero, which is what the hydrogen evolution potential is. So that's why I was saying thermodynamically, it's not too much more difficult to reduce CO2 than it is to evolve H2. It's the kinetics that are the problem. And so really what we're after, again, is we're looking at mimics of enzymes to tackle this problem. And here's one particular enzyme, carbon monoxide dehydrogenase, which is a really interesting system that these researchers a few years back had supported onto an electrode, and were actually able to reduce carbon monoxide to CO2, or sorry, oxidize CO to CO2, and reduce CO2 to CO at the reversible potential. So these are very interesting catalysts, iron nickel sulfide catalysts. And so this is work that we did in collaboration with Ed Solomon in the Department of Chemistry, because we were going to set out to synthesize these types of mimics that were similar to the carbon monoxide dehydrogenase enzyme. But it turns out that when we were looking at the paper, Ed Solomon does actually a lot of spectroscopic work on these, and so he was very kind to loan us some of these materials. And so the question really became, how can we support these onto an electrode surface to pump them with electrons to ultimately reduce CO2? So very quickly, this is our highly oriented pyrolytic graphite surface where we deposit our cubanes on. You can actually see this is atomic resolution on the HOPG. When we drop our cubanes on there, we form a self-assembled monolayer in DMF, where we can do a line scan and show that the width of these molecules, they're standing shoulder to shoulder. They're exactly 1 nanometer apart, which is exactly what you'd expect them to be. But then we immerse this electrode in water, and they desorb off. And so what we've been doing is we've been trying to change that surface, that graphitic surface. We're trying to pit it just slightly enough to get these cubanes to anchor themselves down, but not so much that we cannot get atomic resolution, because we want to be able to count how many cubanes we have on the surface. And so that's exactly what we were able to do by anodizing the surface, by applying a positive potential. We were able to create these little pits and anchor the cubanes down. And in fact, when we bring our STM tip very close to the surface, we can even kick the cubanes out of their pits, and we can see the dark pits left behind. This is after immersion in water, and you can see that the cubanes are still present on the surface. Unfortunately, however, the cubanes do oxidize in water, and that's what this XPS data tells us here. So we can see that the iron gets oxidized, likely to an Fe2O3, and our sulfide peak almost disappears entirely, which tells us that using these types of materials in an aqueous environment isn't the way to go. But that's it's not like all hope is lost, because you can do CO2 reduction in non-aqueous electrolytes. In fact, there's a lot of advantages to doing so, because you can get more CO2 dissolved in your solution. So to wrap things up, again, this is how we're dissecting the problem. You can see some of the approaches we're taking on the semiconductor side of the equation, on the catalysis for reduction, hydrogen and CO2, and for oxidation catalysis. And for those of you who might be interested in photoelectrochemistry, I'd like to also point you out to a paper that we published with a number of other co-authors from different institutions, where we're trying to really standardize the methods used in this field of photoelectrochemistry. In other words, a lot of people have different definitions for efficiencies. They have different methods for measuring photoactivity and whatnot. We're trying to level the playing field so that we can cross-compare samples more universally across the globe. And so I'd like to just point this out to you. It also has a flow chart to help you in your materials development for this reaction. And lastly, I would like to conclude here with the same 3 bullet points I mentioned earlier, that chemical fuels store energy extremely well. So there's a lot of benefits to doing so. We can, in fact, if we can hit our materials targets in the lab, we can, in fact, design chemical plants that can do large-scale production of these fuels. But there's a lot of fundamental issues that we need to tackle, and I hope you guys maybe see something that might be helpful in your research as you develop materials for your case. And lastly, the acknowledgement for the people who do the work who are sitting in the middle row. Particularly, I'd like to thank Jibo Chen, who did the work on the moly sulfide, Yelena, who's been working on the manganese oxide for oxygen reduction, oxygen evolution, and Kendra and Jakob and Ari, who've been spearheading the Cubane project with the intention of studying for CO2 reduction. Of course, our funding, GCEP, NSF, Department of Energy, and Chevron. And thank you guys for your attention.
Hi. So I guess my main question, I guess the most compelling reason for a photoelectrochemical approach to fuels versus a PV plus electrolyzer? And at what price of a PV does that approach, in terms of cost per hydrogen, intersect the cost target?
Yeah. So that's a great question. So let me repeat the question. The question is, if we went back to one of the earlier slides, I had shown a photovoltaic coupled to an electrolyzer. And the question is, what's the advantage of integrating that into one device in photoelectrochemistry? And so it's a great question. Nobody has done a techno-economic analysis on the PV electrolysis system, per se, to my knowledge. That's something that absolutely needs to be done. And for that matter, photobiologic, for the photochemical routes, for all these routes. But the primary advantage is actually the fact that when you're doing water electrolysis, and I'm just going to skip back as I talk, when you do water electrolysis, the capital cost of the equipment is huge. And it's so huge, in fact, that you're going to crank that thing as fast, you're going to run it at diffusion-limited operations to get as much hydrogen and oxygen as you possibly can out of it, which means that your catalysts aren't operating very effectively because, so this unit here, they're not operating very efficiently because you're driving it so hard kinetically. And so the advantage is, if you were to integrate in this device has to be fairly large because you're capturing sunlight, so it has to cover a large area. Then you don't need, A, you don't need such expensive catalysts, and B, you can operate at much lower currents, which means you're getting a more efficient catalysis. So those are some of the arguments. Now, in the end, if this is better, I'm all for it. If this works out to be a more cost-effective way, absolutely, which is why when you dissect the problem into semiconductors and catalysis, we can apply our semiconductors here, and you can apply your catalyst here. So, by dissecting the problem, it kind of universalizes the materials you're studying.
But from an engineering perspective, collecting gases or any sort of reduction product of a large area, you don't view that as problematic relative to collecting?
Yeah, so actually a lot of these schemes were based on buoyancy. So, so just the buoyant gases will, you can take those and separate them, and they're not at atmospheric pressure, but a little bit higher. So it's actually possible. So that was actually taken into account in the techno-economic study.
For more, please visit us at stanford.edu.